Good afternoon, everybody. Before introducing Professor Kim, I want to thank all all attendants to the conference that are on the web. All your questions on the chat are welcome, very welcome. And so now it's an honor, a pleasure to introduce the masterclass lesson of Professor Jae Kwang Kim. Is last dean professor in the Department of Statistics at Iowa State University. He is a fellow of the American Statistical Association and Institute of Mathematical Statistics. He is co-author of the book Statistical Methods for Handling Incomplete Data. He is currently serving as the president of the Korean International Statistical Society. Professor Kim, the floor is yours.
Thank you for the nice introduction, and I'm very happy and honored to give a lecture at the Istat workshop today. So, here I talk is about voluntary survey data. It's kind of a mix of the some lecture and some part of my recent research. Okay. So this is the outline. So I studied a very simple setup. So suppose you have an index set of a finite population with a notation U, and Y is the study variable of interest observed in the sample, and X is a vector of auxiliary variables, and we assume that these X's are available throughout the finite population. And then we are interested in estimating the finite population total, denoted by zeta n, and which is a summation of yi in the finite population, and yi is the realized value of y for unit I. So this is fairly standard notation. And then I will use delta to denote the indicator function of the sample mechanism, whatever sample selection. So if y is sampled and observed, then delta equal to 1, and otherwise it's delta equal to 0. So then this is actually, we have two types of sampling. One is the sample by design, where we know the selection probability, or we sample by chance, which is where the selection probabilities are unknown. And so if the okay, sorry. Let me see whether I can use. If the sample selection is controlled by design, then pi i's are known. And in survey sampling, it is called first order inclusion probability. In the missing data literature, it is called the propensity score. And then I think everybody here knows this Hurwitz-Thompson estimator. So I'll be very quick, but basically, we can, if you know pi I, then we can use the inverse of pi I as the weight, which will give us design unbiasedness, where the expectation is with respect to delta I, not on Y. So that's design-based estimation. So this Hurwitz-Thompson estimator is design unbiased, but it is applicable only when pi I is unknown. And so the design-based framework is very popular in survey sampling, as it does not involve any model assumptions. But in voluntary samples, which is our topic today, pi I is unknown, so we have to do something else. So, okay, so what is the basic framework that we want to use in the analysis of voluntary sample? We can view it as a kind of missing data problem, right? Then basically, we don't observe yi when delta equal to 0. So then the data set we have is xi, and delta I times yi. So that means that we only observe y when delta equal to 1. And then in this missing data framework, then the natural approach is to do prediction. So basically, we use the observed data as a training sample for prediction. So build a model. So that's step 1. And step 2, use the model to predict, right? So that's kind of in a conceptual level of idea of what we can do naturally. And then there's some kind of hidden assumption here, is that one important assumption we want to make here is that, okay, the selection mechanism may be related to X, but not on Y, right? So that sometimes it's called ignorable, or sometimes it's called non-informative, or sometimes called missing or random, depends on how the context. I mean, so anyway, so now what I'm going to do is, rather than doing this regression modeling directly, let's consider indirect of doing regression through weighting. Okay, so then now, okay, so the idea is, okay, we are ultimately interested in constructing weight. Okay, so now, so I intentionally use red color here, omega I, so wi omega I in red color, to emphasize that this is unknown and we want to determine. Okay, so then there should be a constraint on this omega, right? And then natural constraint that we may want to impose on omega I is this constraint, right? So we want to suppose I have, because I know this one, right? I know the population mean of X. So then maybe I should impose a restriction on constraint on omega I to satisfy this equation. So this equation is very important restriction, so that it has a name. So the name is actually, we have different names. It depends on the context. So in survey sampling where we belong to, we call it calibration condition, right? Calibration constraint, or benchmarking condition. And another area, important area is missing data or causal inference area. They call it covariate balancing condition. But conceptually, it's the same thing, right? And machine learning and transfer learning, they call it covariate shift adaptation. So, but anyway, the point is that this constraint seems to be very important constraint, and so that it is also very important. The first step condition, I mean, a key condition that we want to consider in constructing the weight. Okay. So okay, and then because we want to uniquely determine weight, right? So we want to frame it as a mathematical optimization problem. So then the objective function, so then equation 1 is a constraint, right? Equation 1 is just a constraint. There are infinitely many weights satisfying these constraints. So then to uniquely determine this weight, one natural thing is to impose an objective function and construct the optimization problem, right? Constrained optimization problem. So that is a very classical optimization problem. And then you can, because this is a quadratic function, so then solution is not really difficult. So you can apply the Lagrange multiplier method to obtain a solution, right? So L is the Lagrange multiplier that includes the constraint, so linear constraint into the optimization problem. And then this lambda is sometimes called Lagrange multiplier, which is essentially another parameter, right? A known parameter to incorporate the calibration constraint in one. Okay. So then how to solve this, right? How to solve this? Well, take a differentiation, right? So we can take a differentiation with respect to omega I and solve it to obtain this one. Okay. And then, okay, then now originally omega is unknown, but now lambda is unknown, right? So remember the parameter. So omega could be viewed as a parameter, but now we change the parameter to lambda. So then how to solve lambda? Well, we solve it, plug into the calibration equation and solve it for lambda, right? So then we have a closed form solution, which is this form. Okay. And then now because we now obtain lambda hat, right? Because we obtain lambda hat, we plug in and compute the final weight. And the final weight turns out, so this is a closed form weight. And then if you plug into linear yi, it becomes a prediction. So the right side is actually what we started with in the beginning, right? So the right side is what we started with here. So we ended up obtaining the same estimator without really computing the regression coefficient, right? So left side is we solve the problem as a weighting problem, but end of the day, we get the same answer, right? And so okay, that's interesting. So then there must be a model behind, right? So what is the statistical interpretation? Even though the whole discussion here is purely mathematical, right? This is a purely mathematical algebraic problem that I solved, and then I have something that seems to be very related to statistics. So there must be some statistical, model behind it, and naturally the model is a regression model, right? So then what we did indeed is this form. So if you look at this, the error, right? So the weighted estimator, and this is the original parameter. The error can be decomposed into two parts. One is the X part, the other one is the error part, right? So the X part is a C, we can call it C. So mean part can be called the C, and the error part can be called the D, okay? So then the constraint optimization we solved is essentially minimizing expected value of D squared subject to C equal to 0, right? So what does that mean? Well, we basically start with a weighted estimator, weighted linear estimator, and then impose the model unbiasedness as a constraint, and try to minimize the model variance, essentially. Okay, so that's okay, but we probably know here. Many of you probably know that regression weight, the naive regression weight, may be problematic, right? So why? Okay, so if you look at this regression weight, and then this is actually lambda, so linear function of x, right? So then, okay, maybe if x is just one and small, scalar x, this is a linear regression, right? Linear weight. So then if x is too large or too low, then maybe we maybe have some problem. So here's a toy example. So okay, suppose I have a sample of size 5. Very simple toy example. So my x has happened to have 1, 2, 3, 4, 5 value, okay? And then my population mean of x can change, right? It can be 3 or 4.5. We can make it 6. So if it's 3, that means what? Then my weight actually is equal weight. So the regression weight reduces back to the population mean. So basically the regression weight, the role of the regression weight is to benchmark, right? Benchmark to the known total. So then because of this is linear, we got something very uncomfortable weight, right? Which is negative weight. So negative weight is really bothering us, right? So why spend the money to collect the data and take the negative, right? If you think about that, if you have suppose you have a 0 weight, what does that mean? It means that you collect the data and throw it away, right? Doesn't make sense, right? So we really do not want to have a negative weight, first of all. So then that means there should be a we should do something. So, okay. So one solution could be that change the objective function. So so here's one possible solution where you use G. So, okay, now, so previously we used the what? We used the quadratic, okay? Quadratic is a kind of least square. So least square gives a linear regression. But now we want to change, we can change the objective function slightly. So if you use this one, then if you take the negative weight, then log cannot take it, right? So it naturally avoid the negative weight by construction. So then if you use that, okay, so this is kind of Kullback-Leibler type G function and solve the same objective function, right? Same optimization problem. Okay, so we can do the same thing, right? So how to maximize or optimize this? Where we take the differentiation. Okay, so then let's go back to, so if you try to take the differentiation with respect to omega, then this one is a function of omega, and this one is a function of omega. So that means you have something like this, right? So let's go back. So this is what is capital G and small g. So capital G is the objective function, and small g is a derivative. Okay, first order derivative of capital G. Okay, and then, oops, sorry. Then second term is a linear function of omega. So then the differentiation is just you have this. So omega disappears. So it's just a lambda x. Okay. So then you solving this, you will get something like this, right? So G inverse is the inverse function essentially. And so, okay, then now the question is, what is the G inverse function, small g inverse, for capital G, right? Okay. For the choice of capital G equal to omega times log omega minus omega, right? So this is not difficult problem, right? How to compute the derivative of this function is essentially calculus problem. So you can actually solve it, which is this one. So that means the inverse function of log is an exponential function. So that means your weight is indeed this exponential of lambda prime x. So still the same structure, right? Previously we have a linear, but now we have an exponential. But the fact that we express the final weight as a function of Lagrange multiplier is exactly the same, right? So it's structured as exactly the same, just a different variant, right? And so of course, this, if you have this weight, then good news is that we never worry about negative values, negative weights, right? As long as the solution exists, then it should be positive. So that's good news. Okay, now. So what happened? Okay. Now this is not the end. Okay. Now what we want to do is that, okay, now that I have a form of omega, let's plug into here. Okay, plug into here, because my omega is a function of lambda only. So you can plug into here, right? Then the objective function will become a function of lambda only, right? So that is what I did, what we can do. So then if you put it here, basically you have this one and this one. And now this Lagrange multiplier objective function becomes a function of lambda. Okay. And now you can kind of do algebra. So now your capital G is particular this form. So this particular form. So you can actually plug in and do some algebra, right? So you have this is omega log omega minus omega, something like that. And then you have this one. And so then end of the day, so after some algebra, there's some cancellation, and then you get something like this. Okay. And then, so one way to interpret the finding lambda hat is to view it as a, so view this one as a objective function, optimization function of lambda. Okay, so that is this guy. And then, so then how to solve this? Actually, you take the differentiation, right? So if you take the differentiation with respect to lambda, then you get something like this. This is actually calibration equation. Setting to 0 is a calibration equation. So that means this guy is constructing some kind of objective function whose derivative produces calibration equation. Okay, so then how to generalize? So let's generalize further, right? So, okay, let's just start with a very general convex function. That's it. Okay, so you don't have to know G. Okay, I mean, you don't have to specify particular G. So let's start with a general G, capital G, which is as you need to, but you need to have a convexity here, and then that's it. And then solve the same Lagrange multiplier method. Okay, so solve the same Lagrange multiplier method. Okay, then you will get the same solution, right? But now does this, so this is a general G, right? General G. So this is a general small g. And then once you have this, right, you can plug in to the Lagrange multiplier and obtain optimization problem, which is mathematically called the dual optimization problem. Okay, so the primary problem. So there's something called the primary problem and dual problem. So primary problem is this one, the problem with respect to omega. Okay, so the primary problem is the optimization problem in terms of omega, while dual problem is the optimization problem in terms of lambda. They are dual. Okay, and so this guy. So what is this guy? Is essentially we just plug in this omega to the Lagrange multiplier. Okay, to the Lagrange. So omega plug in. If you plug in omega hat lambda here and here, then you will get this one. And so this is the, actually it is mathematically, it is called convex conjugate function. And this law has a very interesting property. So I'm going to explain the meaning of the law more carefully soon. But the point is that the point is that, okay, calibration problem is a primal optimization problem, and we can actually translate it into the language of dual problem, and then this is the key function which we can call which is called the convex conjugate function. Okay, so that is the main message. And what is the interesting part of the convex conjugate function? First of all, so the differentiation of this convex conjugate function turns out to give G inverse. Okay, so that means what? That means, so there's two ways of computing final weight. One way is compute the derivative of G, right? And then compute the inverse function of G. That's one way. Another one is the compute the dual function first, convex conjugate function first, and then compute the derivative. Which one is easier? So that is the kind of story. So this is actually very easy. I mean, still you need to compute the G inverse, but this is interesting. Another aspect of this calibration problem, right? So okay, so actually in mathematics, this convex conjugate function is very famous transformation, which is called Legendre transformation. So what is the Legendre transformation? To be honest with you, I learned this Legendre transformation last year. So if you don't know, you are not alone. So don't worry. So I will try to explain. Try my best to explain. So okay, G is given, right? G, red one, G is given. Okay. Now I can think of the linear line passing through zero. Okay, this should be zero. Okay, A should be zero. Passing through zero, but I will allow nu, the slope, vary. Okay, so you change the slope. So this nu can be small. If it's small, then this one, right? And high and something like that. And then whatever the change, I can always find the biggest difference between the two graphs, the point with the difference, biggest difference. And that is omega star, okay? And then this guy, so low nu is that I view it as a function of nu, and then this omega star is a function of nu because I can change, if I change nu, then omega star will change, right? And so then you have something like this. And that has a very interesting duality of a function. So that is called the Legendre transformation. So I don't know what that's helps you or actually make you feel worse. But let me try to give you some another aspect. So given the convex function, this is defined to be a dual function. I mean, Legendre transformation. Okay, so the Legendre transformation is an application of the duality relationship between points and lines. So the functional relationship specified F can be represented equally well as a set of xy point or as a set of tangent line specify their slope and intercept. Okay, if you change the slope, you can change the, right? If you tangent, and then it gives a different intercept, right? So that gives another characterization of the function. But this one gives a very interesting, component. So here's some examples of the general and generalized entropy. So you have a shared loss and Kullback-Leibler, shifted Kullback-Leibler, empirical likelihoods, scalar Hellinger, and Rayleigh entropy. So whatever the convex function, you can always, there's a convex conjugate function, and then you can basically construct a optimization problem, and whose derivative will give the weight. So that is a kind of idea. So the primal problem, the constraint optimization problem, can be solved by its dual problem, which is the unconstrained optimization problem. So the primal problem is n-dimensional optimization problems, while the dual problem is p-dimensional optimization problem. And so the dual problem is numerically more stable. So that's probably one advantage. So, but end of the day, you get the same answer. So you may wonder, what's the big deal, right? What's the big deal? Okay, I will try to convince you why this is interesting. So here's another direction. So, okay, if you are working on real practical surveys, then you know that this is also important problem, right? How to impose a weight bound, okay, into your final weight, in addition to calibration constraint. So then, okay, you have an additional goal. You want to achieve calibration condition, and also you want to achieve weight bound condition, okay, unequal condition, okay. One real simple way is to apply Huber loss function to the original. So this is original dual function, but you Huberize. Okay, that means what? So now if you write So you may wonder what is the primal original G function. Turns out to be this one. Okay, so what is the interpretation of this one? So okay, if the weight is outside the bound, you give infinity, and you want to minimize, then you will never achieve, right? If you will never achieve this outbound weight if you choose this, transformation. So that gives a kind of another advantage of why Huber's, why the convex conjugate is indeed useful. Okay. So you can actually do Huberization. I don't know. I made up this name, but probably someone already used it. I don't know. So given the G function, okay. Given the G function, you can always add, augment, right, G function by putting infinity to the outside bound. Then you are good. Okay. So then, of course, there's some, some details that you may need to worry about, for example, for variance estimation. So, but this is something that you can, as a kind of a tool, right? Thinking tool to expand your viewpoint of calibration weighting and survey practice using the nice convex conjugate framework. Okay. Okay, I think this is statistical property is probably a little bit too much for, especially in the afternoon, but I will try to be simple. Okay, so now you want to compute the variance estimation, all this kind of thing, and then so there is maybe some more technical part, but bottom line is, okay, here's the final weighted estimator, and the weight supposed to satisfy this, right? And then you are interested in linearizing this one so that you can do some variance estimation. So, okay, yeah. Okay.
Just a short question. Aren't the WIR supposed to work like classical service sampling weights, design weights?
The
WHI.
No, calibration weight, final weight.
Yeah. So don't you want them also require that they are larger than one?
That's a very good question. Actually, I think I have some, I have an answer for your question later. So if I choose this, if you choose this function, you will have a lower bound equal to 1. So if you choose this one, then there's some, yeah. So yeah. So not just the upper bound. Actually, if you have a lower bound to be specified, there's a way. So yeah, thank you. Yeah, very good comment. So okay, so for the linearization, so a point is that weight follows a parametric model. That's the bottom line, is that your final weight is a parametric model, and the parameter is lambda. Okay, and the lambda is actually estimated from the sample. So then you have basically some kind of a Z estimation theory, which is essentially what I'm going to explain. So basically, once you have a parametric model, then you transport all the uncertainty in the final weight to lambda hat, right? So then all your goal is now to do the linearization with respect to lambda hat. But one quick way is to introduce this augmentation parameter gamma and plug in your equation. Okay, so this is equation, calibration equation you started with, right? But now you introduce lambda and then gamma, and this gamma is just a nuisance, right? It's not necessary, because for the gamma hat, this particular lambda hat, sorry, lambda hat, it'll be 0. So gamma hat doesn't really do any role. So this is what it is. But the interesting part is that to carry over the uncertainty of lambda hat to gamma, we need some kind of a special technique. We use this special technique, which is so basically we take the partial derivative with respect to lambda and set it to 0 and find the solution. This solution basically gives you a form of the linearization. So that is something called the Render's technique. But I will just say it. And then, so using this technique, I can get a final result, which is linearization. So your linearization form is very interesting. So basically, your calibration estimator has some kind of looks like a regression estimator, right? You have a prediction, right? Regression component, and this is the kind of error component, right? Residual component, and you have a delta I times this is kind of a weight, essentially weight. So you have a prediction and residual and weight. So that is a very typical result of linearization end of the day. But this is very general. You have given any convex function, you still get the same form. The only thing is that if you change G, you have a different row. You will have a different row. That means you will have a different weight, right? And also you will have a slightly different form of the regression coefficient. And so the regression coefficient is a weighted regression coefficient, but the weight is actually a second derivative of the convex conjugate function. So that is the kind of result. So interesting part is that this linearization, in this linearization, I didn't use any model. Just did a Taylor expansion, that's it. But for this to be unbiased, right? For this to be unbiased, give you unbiased estimator, you need a model. So there's two models can be used. Either outcome regression model, which uses the linear regression model, or a propensity score model, which gives so basically your weight. So this is the form of the weight. Your weight happen to so the inverse of your weight happen to be 1 over the true response probability, essentially. The weight class. So anyway, and how much time do I have? 15 minutes. Okay. So I have 68 pages, and I have so far 36. So I probably speed up, right? So, okay. So I will then skip the theory part. I think that this is a little bit too much, but the bottom line is you have two possible. Oops, sorry. Oh, yeah, two possible models to justify this calibration estimator, and many literature mainly focused on the response model, right? Selection model. So including Danny's talk today. So he's basically tried to build a model for the selection probability. But personally, it's very difficult to find a good model for the selection probability, because do you know when you respond or when you not respond, right? As a function of your characteristic. No, I mean, it's very difficult to model, make a correct model for the selection, whether one person choose to participate the survey or not, as a function of your demographic variable. That's probably not really true. But for why, right? I have a subject matter. So if I know subject matter knowledge, and then we may have a better model for why. which could be built into your calibration. And so then maybe I'd like to start with the outcome model first, and then propose the model as a way to protect against the possible model mystification, rather than starting with the propensity model first and do calibration. So that is my personal personal view of these models. So I will skip this. And a nice thing is that variance estimation is doubly robust, because with the linearization does not really depends on the model. So then the linearization form plug-in variance estimator actually works whether outcome model or response model, sampling model is true. So I'm going to talk a little bit about two extensions. One is the so sometimes you have a model for the response probability. Okay, so suppose you have a response probability, then how to make it as a calibration problem. So that's one potential interesting problem. So that means you basically want to construct this kind of calibration equation end of the day. So that means you want to, right? So you want to construct the conjugate, so dual optimization problem whose partial derivative of this f, which is low previously, is equal to 1 over pi. So given pi, so starting with pi, how to construct, so basically starting from pi, I can construct f, and then from f, I can construct g. So from f, I can construct g. So then this is basically final weight, whose dual problem becomes this one, which will give you this as a calibration equation. So that's one. I thought that's interesting. So for example, so if you have a logistic regression model as a response model, right, propensity model, then turns out that the dual function corresponding, so the f function that gives this satisfying this equation 25, is this one, which is nothing, which is actually first developed by Jichin Tan in Locus. He has many papers extending these ideas, but I realized that what he did is actually doing conjugate, dual optimization. That's it. And then now I figured out that this one, the dual function of this f is this g, which is omega minus 1 log omega minus 1 minus omega. So it looks very complicated, but the point is that if you use this one as a convex function for calibration, it will give you a propensity score weight that is derived from the logistic regression model for calibration. Okay, so that's one way. Another way is okay. Now sometimes I know I have a very good idea. Suppose like in survey sampling, right? I may have a very good idea of pi I in the beginning, and my calibration is to improve the efficiency, not bias correction. So that's a slightly different problem. But in that case, we have a very famous method, first developed by David and Sander, where they basically use the design weight, right? Start with design weight, and then use the convex. So G is a convex function over the. So inside is a ratio, right? The final weight divided by design weight. So you want to minimize the distance, some kind of distance from the design weight. So that's classical approach, I'd say. And the new approach that we propose is that, okay, we are not going to change the objective function, but we will change the constraint. We'll add one more constraint to satisfy the design consistency. So that's a kind of a new idea that I'm very excited about. which is this one. So, okay. So look at this. This is the same as before, right? So this is the same as before. This is the same as before. Now, what is new is that we include this one only. Okay, we include this one, which is this G has to be related to capital G. Okay, so given capital G, I need to compute the first partial derivative, and which is a function, right? And then apply to pi inverse. So that will give another way of constructing the calibration weight. Okay, so I will explain what's going on. So, okay, so equation 30, right? 30 is just the same calibration equation. So that is actually based on the working outcome regression model. So it uses the model. And now suppose your model is not linear model. Suppose your model is more like general, your parameter is more general, then your calibration function may need to be changed to something like this. Okay, so basically if you can use your working model to compute the conditional expectation and then use it as a function of x and use it to the calibration function, calibration equation. So that's the first constraint. What about the second? So second constraint is this one. So what's going on? Why we need this? It turns out that here's a very brief explanation. So think about applying Lagrange multiplier method. So you have an objective function, first constraint and second constraint, right? And then solve this, and then you have this one. And so that means your weight is G inverse over lambda 1 x plus lambda 2 G dx, G di, okay? But the point is that if the outcome, if the propensity score model, so if I know the design weight correctly, then I know that by the law of large numbers, calibration equation will be satisfied asymptotically. So that means my final weight should converge to the design weight. Okay, so that means my lambda 1 will converge to 0 and lambda 2 will converge to 1 in order for G inverse of G di converge to di. That is basically the idea. And so the constraint is called the devising constraint. So its role is to achieve the consistency under the PS model, regardless of whether the outcome model holds or not. And also we have, if you have multiple models, then because we use constraint, so we can just add more constraint. So that means we can handle multiple models if you use this framework. Okay, so toy example. So good news is that we are able to develop our package, so that you can just use it for free. So the package is called the GCAL. So the name is not really fancy, but that's best we can do. So generalized entropy calibration was available, and here's a very simple toy example. So okay, so suppose I create this data, and total of X is 160, 124, and 700. Okay. And then the GCAL, so I can basically choose entropy function, ET, EL, whatever, and then I need to specify the design weight, first of all. So my design weight, initial design weight, here, suppose I have just a 10. Then it does the, it gives the final weight. So basically this GCalib create a final calibration weight, satisfying the constraint. And so we have EL, and then C, cross entropies. So this is essentially, product from the calibration. Yeah, I don't know whether I have a time for show simulation study. 5? Okay, thank you. So here's a simulation study. So this is very simple simulation setup where I have x1, x2, and some nonlinear form. And this nonlinear form, so I can consider two scenarios. Scenario one is beta 3 is 0. So beta 3 is 0 means that there's no nonlinear model, right? The true model is linear. While scenario 2 is the true model is nonlinear, which is more realistic because we never know that true model, right? So then there must be some sort of nonlinearity in the model, but we don't know which nonlinear, right? So, okay, in that case, suppose, okay, because I have only x1, x2, so I could just use 1 and x1, x2 as a calibration variable and hope that this is good enough, right? And then basically what we are doing is we use this one as a working model. Okay, working model. So that means in scenario 1, this working model happened to be correct. And scenario 2, of course, this is incorrect. And I use hierarchy estimator, David and Sandal estimator, GC estimator, which is proposed estimator, and empirical likelihood, and ET, EC, whatever. Okay, so when beta 3 is 0, then the true model happened to be linear, then David and Sandal is slightly better, but the difference is not. So if you look at the RMSE, they are not pretty much very similar to each other. Beta 3 is not equal to 0, then we gain a lot, right? So why? You may wonder why. So I have an explanation. So okay, so actually I have two explanations. First of all, why scenario 1 we are a little bit poor? Because what you are doing is that the true model is that beta 3 is 0. The true model is beta 3 0, but our augmented model approach estimate beta 3. So we try to estimate the 0 coefficient. So that's the price we pay. So the GS estimator pays the price by including the devising constraint, which is this one. So there's a loss of efficiency. But scenario 2, the point is that this guy, even though this model is not correct model, but this additional term helps to capture the nonlinearity in the true model. So because this is basically this additional term is partially correlated with y, conditional on x. So that additional augmented model helps. So the main story is that the benefit, the efficiency gain under the incorrect model is big O 1 over n, while the risk, the efficiency loss on the correct model is a smaller order. So asymptotically, the gain, so benefit dominates the risk. So generalized envelope calibration method is developed as a tool for analyzing voluntary survey data, and different choice of G function can read the different calibration weights. We identify the dual relationship between the regression outcome model and the calibration weighting, and the resulting GC method is doubly robust under the two working models. One is the outcome regression model, and the other is the propensity score model. Our package GCAR is freely available in CIRAN. Okay, thank you for your attention.
We thank Professor Kim for a very interesting, challenging lesson. And now the floor is open to questions, contribution.
Okay, listen.
Okay. Well, obviously, it's very thought-provoking. I need time to digest. So I have many questions actually, but so one question to start with then. So at the end of the talk, you kind of, I'm feeling that you are trying to you're presenting this as a kind of a robust approach, right? So when you sort of adding this additional constraint, when it's not necessary, you don't lose too much, but if it is actually the model, right? But then you had an interpretation, the robustness from the outcome regression model point of view. So if it's a regression model for y is not right, do you have also another interpretation in terms of if the propensity model is not right? Do you have also a kind of a robustness sort of because the simulation is illustrating like if the outcome model underlying sort of things is not right, then my additional term is actually helping me to do something. But do you have a similar sort of illustrations to say there is a propensity model type of justification for the first application, but then my propensity model was not completely correct, but I could also do a calibration using an additional term, and then I also gain something. Do you have something like?
Yeah, there's very sharp question. So actually the presentation is a kind of a mix of two papers. So I wrote two papers. One is a design-based survey sampling and calibration paper. And the other one is a voluntary survey data. So first paper, design-based on the property sampling, is nice because you start with the design-based estimation, right? So you start with the I, and then add a calibration string to improve the efficiency. So that is pretty much purely quasi-randomization or whatever the one direction, right? And then, but in the beginning of my talk, I start with the outcome model, right? So then the reason is that I personally believe that outcome regression model is easier to believe and convince to others than propensity score model, right? So long story short, for the voluntary sample, I would start with the outcome regression model and try to achieve the doubly robust, while the more randomization type property sampling, I start with the propensity score and then try to achieve the doubly robust. So the goal is the same, but where to start is different. Danny? Yeah.
Did you think of the possibility where you can actually account also for non-informative sampling? So what you call the propensity score model depends also on the Y, not just on the X?
I see. Yeah, thank you. So the voluntary, so actually the answer, sorry, I have two papers. So the first paper is start with the design based. So then for example, calibration estimation, right? Is on the design based constraint. Informative or non-informative doesn't really make a difference, right? It's just a design based, right? So in that paper, my short answer is yes for the design based approach. While the voluntary survey data, the answer is no, right? I basically assume that missing a random type, so which is non-informative. So my short answer is no for the second part.
Thank you. So in the calibration work, so you usually have a linear regression outcome model because the constraint is on the total, so it's linear.
Right.
So the whole fault is of the constraint. And usually to move away from the linear regression, you have to like plug there a different function. I was wondering whether at some point, but it was very quick, you just put another constraint. I think it was on the score function, the U. Is that a way of accounting like in model calibration for a more complex model?
Okay, yeah, that's good. So that's right. So basically, the fact that we use the okay, sorry, I see. Yeah, I think my take-home message is that weighting can be viewed as a regression problem, right? So original regression is explicit regression, but while weighting is implicit regression. So that means the choice of the calibration function is actually same as choice of the coordinate in the regression model. Okay, and now the question is, how can we formulate it, the variable selection of the calibration into the framework of the and so I didn't really explain carefully here, but this is kind of ongoing work. But I will nonetheless I will explain my idea. So my current idea is, okay, you can actually include constraint on y. And your zeta is unknown. So you can put x, right? Constraint on x, and put also y, even though you don't know zeta, right? Put that, and then your dual problem, now your dual problem here or here, right? Your dual problem will have a lambda x plus lambda 1x plus lambda 2y. And rho is what? Rho is a convex function. So then this one, loss function, is indeed the regression. The loss function for the regression is regression problem. So that way you can formulate the penalization to so another advantage of this dual optimization problem is that you can directly incorporate all the techniques in the regression modeling into this dual formulation. So, but it's a kind of beginning of the new world. I mean, new exploration. So you are welcome to explore more and discuss with me. But I bottom line is that this dual optimization framework is very useful. Will give us very useful insight, bringing all the techniques in regression modeling into weighting. So that's my.
Further question? Please. A moment.
You talked about for the volunteer surveys. So, in your earlier papers, you had these assumptions that you had to have non-zero or a chance that every individual eye would be included in this volunteer survey. There were some assumptions that I don't know are necessarily realistic. I'm just wondering, do you have to assume the same thing here in this more general approach?
So your question is about the propensity model, something like that?
Yes, so you have assumptions in your earlier work, like the Chen paper in 2020, where you had to have a non-zero probability of being included in the survey. Do you have to assume that here as well?
Right, definitely, right. I didn't really be explicit about that assumption, but I think somewhere, missing a random assumption, even the missing a random assumption should add that non-zero probability in the beginning. Otherwise, this missing a random assumption will not hold. Yeah, that's a very good point. Thank you.
Why is it argmax,
I'm
not
sorry.
necessarily argmin?
Huh? I'm
So
sorry.
when you solve when you write the lambda hat, sorry.
Yeah, I didn't.
So on equation 10 or 12.
I mean,
right?
here.
Yeah, equation 10 or 12, one of them.
I see here.
No, equation 10 or 12. Either
Equation
10 or 12, right? One of those equations.
This
Yeah, for
one?
example, you say lambda hat is argmax. Why can't it be? Is there some simple explanation why I couldn't get it immediately? Why can't it be argmin? Why is it argmax? Is there some?
I see. Okay. So this is a convex function. So end of the day, this is convex. So you minus, right? And then this is, okay? So minus of this convex function. Yes.
There are no questions from the floor, and so I thank Professor Kim, and
you.
I close this session. Oh, there is coffee break.
La terza,
Ok.
Ora la stai fermando via qua.
Questo qui immagino. Sì. Perfetto. L'ultima della...
So, good afternoon, everybody. Welcome to the final session of this day. My name is Piet Daas. I'm from Statistics Netherlands and the Eindhoven University of Technology. I'll try to guide this motley crew of people. It will be an eclectic session because we have topics on whole different ranges. We will start with an overview of the IML4OS project. Frankie will tell you more about that. Then we switch to more of a data-driven topic on IIS data. Marco Di Zio will explain what IIS is. And then we will end up with a topic that touches the first session of this day by Daniela. And hopefully we will be there on time, and then there's an opportunity for questions as well. So with that, I'll ask Frankie to kick off the session. And I'll try to watch time, so I will send some signals to the people presenting.
Hi, good afternoon. I'm always very conscious when you're at the last session that you're between people either going home or the bar or a meal. So I'll try and be concise. I'd also like to say, for those of you that love algebra, this is not the presentation for you. I don't have a single equation in any of my slides, so very sorry about that. So this is quite a high-level view of the project because we're still fairly at the beginning. So for those that don't know you, you can see I do have an Italian name, Francesca. I am known as Frankie though, so my mother hates that. But so if you wish to call me Francesca, especially as I'm in Italy, that's fine with me. I'm the Chief Information Officer at the Central Statistics Office, but I do also within my remit look after methodology and data science and AI and machine learning, hence my presence here today. So just to give you a little bit of background on the project that I'm going to talk about. So about 18 months ago, Eurostat put out a grant or a call for a grant to set up a one-stop shop for AI and machine learning for official statistics. So Ireland got together with lots of other countries, including Istat, to put together a consortium. So we're funded by an EU grant, and the project kicked off in April. It's actually a 4-year project, which is quite unusual for SNET. It's quite long, and it is one of their bigger projects in terms of funding. So there's quite a lot of pressure. Mauro at the back, just to, no pressure there. So what are we trying to do? This is really about providing a set of resources around AI and machine learning. And we were just chatting beforehand, and part of what we're doing is really about creating community as well. So we're trying to develop and evolve a set of capabilities that we can share across the EU and indeed potentially beyond that as well. We're looking at providing a sandbox so that people that don't have the infrastructure within their own countries can potentially at least do some experimentation reusing the platform that we're providing. We're looking to provide guidance and maintenance and provide training and active support for countries. And as I say, it's very much about creating community as well. We want to share ideas, we want to share experiences, we want to share successes, but we also want to share failures. As we all know, not everything we try will always work, so it's important that we learn from that as well. And it's very much about stimulating innovation. And very importantly, we want to try and enable that transition from experimentation into production-ready solutions, which often can be quite challenging. So to be a bit more specific, we're basically trying to provide a framework so that as countries want to look at developing their AI machine solutions, they have a framework that they can start off with. And obviously, this is very much in the context of official statistics. We want to provide Europe, staff across the whole of the EU, access to some proven solutions and resources so that you can take those. You don't have to start again from scratch. And that's what we're trying to do. We all know we're working with limited resources, so it doesn't make sense for us each to be looking at developing similar solutions within each country. So we're trying to make sure we can provide those resources to you all. And part of this is also about, by providing those resources, providing that information, those successes and those failures, that we can really encourage countries to innovate. Because, whilst AI machine learning is, it's massive, but we do believe that there are benefits that can be realized from its use. And we want to give people the confidence to go and try things. And of course, as I mentioned, we do have limited resources. So we're trying to provide economies of scale through cooperation, not just within the EU. We're very keen, and we've begun to start reaching out to the UN. Some of you may possibly tell from my accent, I'm actually not from Ireland originally. I'm from the UK, and I used to work for the Office for National Statistics. And now that they've signed an agreement with Eurostat, we can bring them slightly more into the fold. So we're keen to leverage with the ONS and indeed countries such as, Australia and New Zealand and Canada in particular, who have a lot of expertise in these areas as well. So these solutions aren't just for Eurostat. They are about building a really strong community sort of anywhere across the world. So who is involved? There's all of these countries. I won't go through all of them, but there's 14 different countries involved in the consortium, so which is a great number. So it's basically about half. The EU and Greece have reached out, and they're keen to get involved as well. So you know, we're very keen to reach out to the countries that might not be formally in the consortium. So what are we doing? So this is just trying to give a bit of an overview of how the project is working. We have a number of work packages that are what we call cross-cutting. So they're trying to either enable the use cases, or they receive information and training and knowledge from the use cases. And very much at the heart of these are these use cases. So these are individual projects that are looking specifically at different elements of how we can use AI and machine learning in official statistics. So just to give you a little bit more information about each of those, obviously the most important, because Ireland are leading on it, but actually potentially the most boring is the coordination. So we do all the boring stuff. We do all the project management. We annoy Maro and people like him with asking him to fill forms in and how are they doing, and same for Peter. But it is quite important to make sure, obviously, that we can we provide that overall management of the project. Very importantly is comms and engagement, which Istat are leading on. And this is both within the project, but even more importantly, outside it as well. So they very much are helping us to create that outward-looking element for the project. Our colleagues at ONSI are providing the sandbox. They have a platform called Anexia, and they're making that available to anybody that wishes to use it. They are the most advanced work package. They've made the most progress in the sense of official milestones that they've delivered. We also have, obviously, we're very interested in understanding how AI and machine learning is being used now, but also potentially how it could be used in the future. So we're really looking to understand what that ecosystem is, and Status are leading on that. And then all of the work patches are really important, but Peter's leading on this one, so I have to say how important this one is. And this is about standards. So this is about how we pull together those resources and really think about how do we get from that experimentation into production as quickly as possible. So it's really about industrializing AI machine learning within statistical offices. And Poland are leading on providing that knowledge sharing and training as well. So what are the individual use cases? So we have a number of different, we tried to cover different areas in AI and machine learning, and Lee Chun and I were discussing a little bit about Earth observation data and satellite imagery. And this is really about understanding what models are being used on Earth observation. Can they be made more generic so that other countries can actually take those models and use them within their area? So there's quite a lot of research going on about understanding how they're used at the moment. We've got another work package which is focused on editing, which I think is an area that many offices perhaps are beginning to look at. How can we make statistically valid and efficient editing using AI and machine learning? We've got one on imputation. So this is looking almost at each stages of imputation. So is there anything that we can do to impute almost before we send out surveys? Is there anything that we can use AI machine learning in imputation within the sample that we've drawn? If there are missing units or missing variables, can we use AI machine learning in that area? And then could you think, is there a way that AI machine learning can effectively take that sample and then impute it for a whole population? So there's a number of different facets to that use case. Again, I think this is something that perhaps quite a lot of countries are beginning to look at, but how can we use AI machine learning for classifying and coding? So things like NACE2, COICOP. And one of the areas they're looking at is how you try and adjust for different languages, because if you're trying to come up with EU-wide solutions, language and things like text is obviously quite a big barrier. We've also got a use case which is looking at how we can estimate firm level supply chain networks. So how can we look across countries and see how those supply chain networks work and how we can try and make sense of the data that we're receiving. I would say that LLMs is probably the biggest thing in technology over the last 6 to 12 months, ever since ChatGPT came out. I don't know, I've heard this LLMs talked about more than anything else. And again, in statistics, certainly in Ireland, we're using it to help us move from SAS to R, and we're using that to help translate the code. And some statistical offices are beginning to look at it with regard to their websites as well. So this work package is really trying to understand almost the potential for LLMs, what parts of the statistical office could they be used in. And then finally, we're looking at how can we generate synthetic data, how can we, I suppose, increase the utility of synthetic data and make it as realistic as possible, whilst obviously still maintaining privacy. So in terms of, I suppose, it's a methodological conference, and what we're trying to do here with regards to the methodological aspects of what we're doing. So, we've been using artificial intelligence in statistics, or certainly machine learning in statistics, for a number of years. But now it's trying to get to a point where it needs to start moving to the same solid, robust basis as all of what we've been hearing about today in terms of surveys. So having reliable methods, repeatable methods that are well understood and produced. So I think we're beginning to get to the need to be able to provide that, I suppose, consistent methodological guidelines. Clearly, I'm not implying that the current uses are not methodologically sound, but it's how can we try and get those methods as well understood as some of the ones that we currently use today in survey production. Another key aspect of this is, there isn't, as we all know, with the current methods, there isn't a one size fits all, but what we try and do is come up with generalized knowledge. We can identify the norms, identify best practices, that they can be used as a basis that others can then take and make adjustments to as they need to for their countries or for the individual statistics that they're producing. So that's what we're trying to do. How realistic and how far can we make those standards available? How far can they be pushed before they're not methodologically sound? And also, as I've mentioned before, just the importance of having those standards so that we can facilitate that transition from experimentation into production. So what are the key aspects in this? In terms of standards, it's looking at things that you're all incredibly familiar with. How do we make sure that we apply clarity, interpretability, transparency? Data quality is incredibly important for AI and machine learning, as it is for all of the statistics we produce. But when you're dealing, as you all know, with masses of big data that's not being collected for the purpose that we are attempting to use it, the quality issues are of a different nature to those than from surveys. So that's incredibly important. Just like everything else we do, we need to be able to reproduce it. So, making sure that it's auditable. And ethics, as always, still needs to be incredibly at the heart of what we do. As sometimes is said, just because we can do something doesn't always mean that we should. So we want to make sure we're thinking about the ethical use of AI and machine learning as well. So in terms of the methodology, at the heart of what we're doing is those robust, reproducible methods, making sure that what we're doing is unbiased, because again, as you all know, these algorithms are only as good as the data, and if the data is biased, then the outputs will be biased, and likewise, the people coding have their own bias as well. So how do you try and make sure that our algorithms are statistically robust and are providing us with those valid statistical outcomes? In terms of the work package that Peter's particularly involved in, it is thinking about the practical aspects. So how do we set up machine learning operations to really embed, we have the GSBPM. Do we need to adjust that? Because now we're in a world of machine learning operations, which is slightly different from perhaps the setups that we're traditionally used to. It's important to have AI machine labs. Again, just the sheer size potentially of the data that we're using in AI machine learning, it just takes a whole different world in terms of processing power. So how do we try and provide that infrastructure? And is there an opportunity to share that more widely? And as I said, making sure that we take all of that into account so that we have got that regular repeatable pipeline into production. So in terms of the current status, where are we? Every work package has commenced work. And I'm not sure this is the latest version of slides, but I'm going to keep going. I did make an adjustment. So each one has commenced, and we do have a project dashboard, which is provided on the Eurostat platform called Cross. That QR code will take you to that platform, and you can go and find out more about the project. And we do have a newsletter launched. Are the slides going to be sent out after the presentation, after the conference? Am I getting nods? Well, they just because they don't have the email address, which was specifically asked to put on. But anyway, so but if you click on that, then you'll be able to find more about the project. My colleagues over there have provided our first newsletter, which went out in September, and another one is due out soon. So what have we been doing in terms of the work packages? Research has started across all of them, and some early examples are doing that comparison I mentioned around Earth observation models, so we can figure out which ones can be generalized. The supply chain network is taking a solution that a Belgium software solution and Oxford University have been working on, and beginning to apply that to supply chain networks in Portugal and in the Netherlands, so that we can see again how they can be applied more widely. In the synthetic data use case, they started looking at how can that be used to help with privacy risk management. And in the text to code, they're beginning to consider which use cases likely to be things around NACE revision, as that's something lots of countries are working on at the moment. And in the editing work, they're beginning to look at error detection and editing in large data sets. But every other work package is underway, and they are now agreeing the specific use cases and then the associated methodologies. But as I mentioned at the beginning, the sandbox is now available. And importantly, France is about to provide information and instructions on how that sandbox can be set up in other countries. Because this work package is not just about the sandbox itself, it's about providing resources, materials, scripts that others can create their own infrastructure. So what are the key events? We had the first one in Germany in April, where we had the kickoff, and we're going to be at NTTS next year. We have a project meeting, but there is a session on NTTS, which Istat are leading for us. So please do come and see us at that conference. We also expect to be at the Quality Conference in 2026. We'll be back at NTTS in 2027. And the one that most people seem to be excited about is the closing conference in Dublin. I think it's got something to do with Guinness, but that will be a conference where we'll be able to share everything we've been doing. So if you want to learn more about it, that's not quite the right email for the for the newsletter, but I'm sure we can circulate it. But if you do use that email address, we can forward it on to Julio at the back, who's now leading on comms. And we also are on LinkedIn, so please do find us. It's SNET AIM-L for OS, so please follow us on that as well. And that's it. So quick. I don't think that was 25 minutes.
Okay, that was exactly 20 minutes, so that's great. Now, Marco Dizio will present work on the statistical use of AIS data. And AI in this abbreviation doesn't mean artificial intelligence. It's something called automatic identification system data.
Okay, thank you, Pete. And this is the first slide, and you are very used to see very what? So I can. Okay, now start again. So this is the first slide, and I want to make the first remark about the long list of names. You are used to see this long list of names in the Istat works, but here I have to say that the first lessons I've learned working on this big data, non-traditional data, is that is needed conditions in qua non, in a sense, to have a team that is composed of different competencies, statisticians and people expert of the matter and so on, IT expert. Otherwise, you cannot succeed. So this is just the first slide. Imagine the rest. So, okay, I will jump this one. So a bit of context. So we are talking about the fact that Istat must provide Eurostat with maritime transport statistics, and that are statistics on transport of goods and passengers carried out by vessels engaged in commercial activities. So this is the survey we are talking about. Currently, these numbers are produced by an integration of a complete enumeration survey of shipping, where the respondents are agencies and owner ships, and administrative data taken from port authorities. So there is a request by Eurostat, improving timeliness and quality, as every time, of course. On the other side, we go on the internet. You can type a name or whatever about ships, and you can see this picture. This picture is the traffic of vessels. In this case here, you see the Mediterranean Sea, and all these arrows represent vessels. The direction, you can the name, velocity, and whatever you want about each single vessel. So the game is quite easy, no? I mean, you see, okay, take this and produce your statistics. In fact, we try to do. All these symbols, all these vessels and the position are taken by based on these AIS signals that are the signals sent by each single vessel for security reasons. And so every, I don't know, 10 minutes in some very frequent intervals, you have this signal saying what's the name of the ship, where is the position, the velocity, and so on, the speed, and so on. So, okay, let's try to do. So the column feeling is it's easy, but in practice, it is not. So which are the main problems? First of all, the data availability. Every time we talk about big data, non-traditional sources, but the first step is to get this data. Then we have to manage. There is another problem, IT problems. Then we need to transform for our purposes, and we have to check the quality. And this is the steps we have taken into account in this work. First of all, data availability. Data are not free. I showed that picture, but we are not able to get those data without paying to the company that made that elaborations. Fortunately, recently, the UN made it available for free for members of committee of experts on big data. So the first step is okay. The second is data management. It is not straightforward. The data are in cloud. It is not possible to download a huge amount of data. So there are a lot of, let's say, technical problems. But now we are able to manage with that. So these first two steps are okay. So the next step is to transform those data for our statistical purposes, okay? In fact, even with data at hand, we are now able to get data and to manage them. It is not easy to produce statistics we want to produce, to provide. In fact, they are signals, and we need to transform data to have roots. For instance, for counting how many vessels docked in a port. To do this, we need to derive two important elements to understand the route of a vessel. First of all, we need to delimit a port. And the second, from the signals, imagine you have, for each record, you have the name, the position, the speed at that time. So repeated many times for each vessel. And you have to define if the vessel is docked or not in a port. So these are the two main elements. Let's go to see something about how we define the port. First of all, we choose this way of georeferencing the surface. That is the H3 system. That is the one, the Uber classification, and that divides the surface in polygons, in hexagonal polygons. And starting from, you see the red one and the part, that is the hexagon corresponding to the coordinate of the port, we augmented with other hexagons, and that potentially depict the area of our port. And these hexagons are estimated through the AIS data. Every time we see a ship stopping in that place, more than a ship, of course, we suppose, if it is close to this coordinate, that it is an area where the ship can dock. Then we have to transform the signals to route, to the voyages of the ship. You see here you have the data. No, this is a record, one single record, and we need to transform the single records, each set of records in a voyage. And for doing this, we took into account the speed of the ship, and if the speed is 0 and the position is in hexagon of a port, so we suppose that is an arrival or a departure. It's the beginning or the end of the route. And this is the transformation we did to make use of this data for statistical purposes. Once we have transformed this data in such a way that we can elaborate for our purposes, of course, we need to ask for the quality of those data. And are there any gaps in this data, or in a sense, what's the quality for our statistics? So we started with some analysis in order to see if there are some problems. Of course, imagine that you have a lot of these records and transformed records and so on. So the first analysis was made by comparing aggregates, by comparing the number of arrived vessels in a port, estimated by using AIS data, and what we have in our official procedure that I remember is composed of administrative and survey data. And by looking at this, let's say, the biggest differences, we we drilled down data in order to see if there are some specific reasons, some systematic errors for explaining this difference. Then we were able also to link data we have an official procedure with those transformed and obtained by AIS data, because there is an ID identification, an ID code that identifies the ship. So we made a record linkage and also made some analysis by looking at the difference at micro level. So we saw that there are these three big problems. The first one is that in AIS data, short and frequent routes are undercounted. Imagine ship going from the one port to, I don't know, an island, for instance, very close. And many times, I don't know why, but in our data, we saw that there is an under coverage of the number of these voyages, these routes, not routes, voyages. And then we saw also this other problem, this other problem that is the interruption of signals. So imagine you have a lot of records, I don't know, let's say every 10 minutes, and then the next record is after, I don't know, 1 hour, 2 hours, 1 day, or whatever. So there is an interruption of signals that we have to understand how to deal with. And finally, there are some anomalous routes. I don't know, people going from, let's say, I don't know, Naples and to Istanbul and then to Genoa in, I don't know, in a few minutes. Yeah, exactly, anomalous routes. So for the first, we try to deal with these problems. Of course, for the undercount, we couldn't, let's say, correct data by looking at the errors. We need to take into account when we will use in the production process. But for the interruption of signals, we need to transform these interruptions in what is a problem for our statistics. So I wrote here from interaction of signals to relevant missing data. And so we select a segment as a potential docking event. These are the problems for us. If the time interval between signals exceed the maximum threshold, a long time, but the average velocity is less than a minimum threshold. It means that it can be that in that time the vessel stopped somewhere in some port, and then took again the route, the voyage. Okay? So there are potentially cases of vessels docked in a port, potentially. So just some numbers. The experiment we did on the first quarter of 2022, 14% of the voyages had this potential problem. We developed some methods for imputation, for imputing the port, if it is the case, of course. And we developed two kind of approaches. A deterministic approach is the first, where we use the information we have in the AIS data, because in the AIS data, we have the destination field. Where is the destination? And sometimes I mean, we know that there are some mistakes in this, and we see if we try to impute this destination field for this problematic routes, if it is, of course, consistent with the time and the location and whatever. Otherwise, we try to impute with the most frequently destination of the ship in that route. Of course, it must be, again, one more time, consistent with the information we have. And for the most critical cases, we have also developed deep learning methods for imputation. Deep learning, because in fact, a lot of literature has been developed in this context. And you can imagine that given the difficulty and the complexity of the problem, because you have direction, you have a lot of signals and so on, this kind of deep learning and more machine learning, more in general, deep learning algorithms can be useful for this context. And so we developed, we did some experiments with this one-dimensional convolutional network and long short-term memory network. And the first experiments, the estimated accuracy is around 82%. So we are quite happy about that. And we have to understand how to use these two methods integrated in a pipeline. But anyway, we developed these methods. The other problem is about the anomalous routes. This is a picture showing what I said before. We don't understand very well from year to year in a while, so it is clearly a problem. So to understand which are anomalous routes and probably errors, we need to integrate space and time information. So traditional outliers methods are not so common for this problem. So we try to reduce this to a univariate outlier problem, and we, in a sense, we use the average speed, that is the speed and, of course, the space. And when this average speed is greater than a threshold, we select this like a problem. I mean, if a vessel got 100 kilometers, it's not this in miles, but 100 kilometers doing, I don't know, it's not possible. I mean, it's not a velocity, a speed for a ship. So this was to select the outliers, but it is not the only technique that we have to introduce for dealing with these outliers, because of course here you can see that you are able to, with this method, you are able to see the jump. Oh, okay, here there is these are the speeds. It's a very high speed, but of course if there is a signal, this jump, and then the ship stays in that place, the subsequent points will not be addressed as outliers because they are conditioned on the time before. So we did a sort of cyclical application of the algorithm, first deleting and selecting and deleting step by step. This is a representation of the algorithm, the cycle that algorithm do. And this is a picture. This was the first picture with the anomalous root, and this is the cleaned picture, deleted with the root deleted. So finally, now we can use AI as data. That's the good news. We did all this long and I would say hard work to do this, but the next question is how? Okay, this is the second part of the movie. I hope that probably next year we will have the end of this. But now we have already some encouraging results also in practice. First of all, we can improve some statistical figures for sure. For instance, the offshore platforms. You can see here that here we have platforms. The location of the offshore platforms has allowed the identification in AIS for 2022 of almost 5,000 arrivals. The official procedure slightly more than 230. Because these are particular, I don't want to say ports, but particular places that our survey is not able to deal with in a proper way. So here we have right now just first results, and we can do, for sure we can do better also in other situations. But we are also using as a kind of auxiliary information for validating our data and for checking the errors, the potential errors in our official procedure, because every time we have, of course. And this is an example. Here we have, these are 20 vessels. Each one is a different vessel number 1, number 2, and so on. And for each vessel, we have the number of arrivals, sorry, the number, yes, of arrivals, according to the 3 different sources. That is the survey data, let's say, Tramar here, PMIS, that is the administrative data, and the ones we have counted with AIS. For instance, in the first 2 ships, we see that there is an agreement between administrative and AIS data, while there is a big difference between the survey and the other 2. We went to look at our data, drill down, as I said, and we found that in fact there was a problem. If I don't mind, if I remember, it was a kind of duplication problem. But thanks to these other source, we were able to understand better where it was the problem. So that is another use of this kind of data. Of course, we need to understand and to go on with this kind of analysis and end up with a more systematic way of introducing this data into the production process. So as I told you before, we are at the end of the first half of the movie. So we are able to manage this data. Now we have to understand how to use in a better way this data in our production process. That's the end, not of the movie, but of the presentation. Thank you.
Thank you, Marco, for a very interesting presentation. I have more answers than questions. So it's one of the biggest data sources there is. Yes, so that's the intriguing part. But we have another presentation from Daniela Marella on statistical matching and informative sampling. So Daniela, the floor is yours.
Thank you. Thank you. Good evening to everyone. What is the aim of this talk? Okay, the aim is to deal with the statistical matching problem under non-ignorable sampling and response. And this is a joint work with Danny Pfefferman. We assume that we have two samples, A and B, from a population generated from a joint distribution FP governed by a parameter theta. And we assume that the variable X and Y are observed in sample A, and the size of A is NA, and the variable X and Z are observed in sample B of size NB. Well, the aim of the statistical matching is to estimate the joint distribution for the variables of interest, that is the joint distribution of X, Y, and Z. But the problem is that the lack of joint observation on Y and Z implies that the statistical model is not identifiable unless under strong assumptions, which generally are hard to confirm. Then several alternative approaches have been proposed in literature to overcome the identification problem. The first approach assumed that the two not jointly observed variables Y and Z are conditionally independent given X. The second approach assumes that external information regarding the relationship between Y and Z is available. For instance, a small sample C where X, Y, and Z are jointly observed. And finally, the third approach analyzes the uncertainty regarding the joint distribution function of X, Y, and Z. This means that the last approach defines the class of plausible model compatible with the sample information, that is compatible with the marginal distribution of X and Y and X and Z that we can estimate from sample A and B respectively. Now, the aim of this talk is, first of all, discuss the statistical matching under the conditional independent assumption, assuming that the two samples A and B are informative and are affected by a not missing at random no response, and we propose an approach based on empirical likelihood. Second, we drop the conditional independent assumption. We analyze the uncertainty in statistical matching. And finally, I will show you some result of an application to SHIV and HBS datasets, where SHIV is the survey on household income and wealth run by Banca d'Italia, and HBS is the household budget service survey run by Istat. Okay, what is the basic idea of the empirical likelihood? The basic idea is to approximate the population distribution by a multinomial model, which support is given by the empirical observation, that is given by the sample data. The main advantages of this approach are, first of all, it does not require to specify the population model, and second, it facilitates the use of calibration constraints. This means that if the population mean of some covariates are known, we can insert this information in the maximization of the likelihood, of the empirical likelihood, and then we can improve the accuracy of survey estimates. In the sequel, we assume that the two variables Y and Z are continuous. X is a discrete variable taking big K distinct values. And then under the conditional independent assumption, the joint population multinomial probability of unit I can be factorized in this way. Okay, because under the conditional independent assumption, the joint distribution of Y and Z given X is given by the product of their marginals. And okay, the sample, it's possible to prove that the sample empirical likelihood based on A union B is given by this expression, where the models appearing in it are the sample models. Then, for instance, with regard to sample A, Py given xa and Pax are the sample model of y given x and x. And because under informative sampling, the observed outcomes are no longer representative of the population outcome. This means that the sample model is different from the population model. And in particular, the sample models depend on the population model and depend on this probability, on the sampling probability. Now, this probability can be estimated according to this relationship outside the likelihood by regressing the sampling weights against xi, yi. And then the estimate can then be inserted in the empirical likelihood, and this means that the likelihood needs to be maximized just with regard to the population parameter, that is just with regard to this probability under this constraint, where the last constraint is the calibration constraint because it is due to the knowledge of the population mean of X. And now we assume that additionally to notice that after having estimated the population parameter, we can test the null hypothesis that the sample model fits the sample data can be tested using classical test procedure because the sample model refers to the observed data. Now, additionally to informative sampling, we assume that A and B are subject to a not missing at random no response, and then we obtain empirical respondents likelihood. The form is very similar to the sample likelihood, but the big difference is that the models appearing in it are the respondent models. Okay, then the respondent, for instance, for the sample A, but analogous expression can be obtained clearly for sample B. We have that the sample model for y given x, the respondent model for y given x depends on the sample model and on the response probability. Then we have that the respondent model is different from the sample model, and the sample model is different from the population model due to the informativeness of sampling design. Then, clearly, how can we estimate the quantity appearing in the empirical respondent likelihood? Then, first of all, if we assume that the response is independent of sample selection, then this means that this equality holds, and then we can, as before, we can estimate this probability outside the likelihood by regressing the sampling weights again xi, yi, then using the sample data in A. The same for clearly for the sample data in B. And with regard to the response probability, we don't know the response probability, then we need to estimate them, and then we need to introduce a parametric model, then, for instance, a logit or probit function, and clearly the model depends on no parameters gamma A. And in sample B, clearly the response probability will depend on a no parameters gamma B. And now this means that the empirical respondents likelihood needs to be maximized with respect to a larger set of parameters, that is the population parameter, this probability, and the response parameters in A and B, respectively, under this constraint. The last constraint is the calibration constraint, assuming that the population mean of X is known. Now, and in order to estimate the empirical respondent likelihood, the population parameters, we use a profile likelihood. That is, we fix initial estimates of the population parameter and we maximize the profile likelihood with respect to the response parameter. Then in step 2, we substitute the estimate of the response parameter in the empirical likelihood, and we maximize with respect to this probability, respect to the population parameter. And this completes the first iteration in the estimation process. In the second iteration, clearly, the estimate of the population parameter obtained in step 2 are assumed as no, and then we re-estimate the response parameter, and so on until convergence. Now, clearly notice that the empirical respondent likelihood is essentially given by the product between the empirical respondent likelihood for sample A, the first part, and the empirical respondent likelihood for sample B. Okay, then this means that we obtain two estimates for the population, for the distribution of X. That is, we obtain two estimates for the population parameter PKX, the first one for sample B and the second one for sample A. And then we need to harmonize these two estimates, and we can use alternative methods. The first one, we can consider a linear combination of the two estimates obtained from A and B respectively, where the coefficient lambda is a coefficient in 0, 1. For instance, a plausible estimate could be this, that this lambda is given by the ratio between the size, the sample size of A over the sum of the sample size of A and B. Another method, and we can take the value of lambda, minimizing the variance of this estimator, but this means that we need variance estimate of the two estimators obtained from A and B respectively. And then in order to accomplish this, we can use the resampling method for finite population. And finally, another method is the following. We can replace the empirical likelihood, the respondent model, by this linear combination. But this means that we need to maximize the empirical respondent likelihood with respect to the population parameter, with respect to the response parameter, and also with respect to lambda. Okay, now once the parameters, the population parameter have been estimated, we can reconstruct a fused data set with joint observation of X, Y, and Z using the following three steps algorithm. First of all, we generate n tilde observation from the estimated distribution of X, and then conditionally on X, we draw at random a value of Y tilde from the estimated probability function on Y given X, and a random, we draw at random a value of Z tilde from the estimated distribution of Z given X. Now, the problem is that the conditional independent assumption often is inappropriate. And furthermore, the conditional independent assumption cannot be tested by data. And then we drop this assumption, and according to the methodology proposed in Conti, Marella, Scano, we define, first of all, the class of plausible models for the variables of interest when no information is available and under the constraint that the variable Y is less than or equal to Z. Next, we compute an uncertainty measure, quantify how broad, how large is this class. And finally, we propose the iterative proportional fitting algorithm to choose a matching distribution from the class. Now, the statistical matching problem requires essentially the estimation of the marginal distribution of X and the estimation of the joint conditional distribution of Y and Z given X. Now, the problem is the second point, because we don't have joint observation of these variables. And then if no auxiliary information is available, the only valid statement is that the cumulative distribution function of Y and Z given X, K, is between these two bounds. They are differentiable bounds, okay? And clearly we can define a natural uncertainty measure conditionally on X, given by this expression. We take just the difference between the upper and the lower bound. Here we consider a weight function given by this, that is, we assign large weights to interval with larger marginal density, but alternative weight function can be used. And from the conditional uncertainty measure, clearly we can define an overall uncertainty measure by the average of the conditional measure. Now, the problem is that had the class of plausible model, that each distribution in the class of plausible model can be taken as a matching distribution, that it can be taken as a surrogate of the actual distribution, since the sample data do not allow to discriminate between alternative models. But the problem is that if auxiliary information is not available, the class of plausible distribution is too wide and to be usable in practice. And then this means that in the uncertainty approach, the availability of auxiliary information able to exclude some models and then to reduce the class of plausible model with a consequent reduction of uncertainty is crucial. And then for this reason, we consider external auxiliary information, assuming that the variable y is less than or equal to z. Then we can compute the new Frechet bounds, and given where this is the upper bound, this is the lower bound, and finally, clearly we can, under the constraint, define the conditional uncertainty measure and the overall uncertainty measure as before. Now, clearly, the final step is to choose a matching distribution from the class, and we propose the iterative proportional fit algorithm. Now, the point is that the use of external information is crucial. That is, the larger the uncertain reduction due to the use of auxiliary information, the more plausible the choice of a matching distribution from the class. With regard to the iterative proportional fit algorithm in the empirical ACLU context, we proceed according to the following step. First of all, we discretize the continuous variables y and z. Next, we estimate the marginal of the discretized variables using, according to this formula, then using the estimate obtained by the maximization of the empirical respondent ACLU. Then we define the contingency table where the marginal are fixed, are this estimated marginal, and clearly after having defined the contingency table, now we have to introduce the structural zero in the table. That is, we have to put 0 in the cell that does not, don't in the cells that don't satisfy the constraint, that we insert 0 in the cell where y is larger than z, and clearly we consider the midpoint of the variables. And for the remaining cells probability, we define the initial values according to this expression. That this means that we introduce a quasi-independent assumption. That is, this is the product, this is between the two marginal, the marginal of y given x and the marginal of z given x. Now, I will show you some results regarding application to achieve an HBS. In Italy, information on household income and expenditure is provided by survey on household income and wealth run by Banca d'Italia and household budget survey, but no single data source containing information on both income and expenditure exists. And then we consider the 2010 wave for SHIV and HBS2, and this is the sample size of SHIV and this is the sample size of HBS. Now, we assume that the matching variable X is the household size, taking the value 1, 2, 3, and 4 plus, and value larger than 4. Y is the expenditure, Z is the income. This is the calibration constraint that we assume that the average of household size is equal to 2.4, and we harmonize the two estimates of Px k according to this linear combination where lambda is equal to 0.27 is given by this expression. Now, the response rates is about of 62% in SHIV and HBS, and the response, we can assume that the response is explained by the size of the household and the income, and in order to reproduce a response rate of about 62%, we generate the response set from SHIV and HBS according to a logistic model with these parameters. This is, for instance, with regard to gamma A, this is the parameter corresponding to X, this is the parameter corresponding to Y. Now, first of all, under the calibration constraint, because we assume that the mean of X is known, in the following table we report, first of all, the Istat estimates of household size distribution in Italy in 2010. Then we report the estimate obtaining ignoring the informative no sample on design and the no response. And then we report the estimates of X distribution, taking into account just the informative, the sample and design. And finally, in the last column, we report the estimate taking into account both processes, that is the sample and design and the not missing at random no response. And finally, we compute the Hellinger distance between the Istat estimates. They are assumed as true values, as a benchmark values in order to evaluate the performance of the other estimators. And then we compute the Hellinger distance between the Istat estimates and the other estimates. And we note that the Hellinger distance decreases from 1.76 to 0.885, and the minimum value is achieved when sampling, design, and no response are taken into account. And finally, with regard to correlation, notice that in HBS and SHIV, the correlation between X and Y and X and Z is equal to 0.38 and 0.31. And then we estimate the probability, the conditional probability on Y given X and Z given X. We generate a fused data set, and then we consider two scenarios. In the first one, we ignore the sampling design and the no response, and we obtain this correlation. And in the second scenario, we take into account both processes, and we obtain this correlation that are closer to the true one. Notice that in SHIV, in the survey of household income and wealth, there is a section regarding the household expenditure. Then we can obtain from this survey a estimate of the correlation between income and expenditure, and in SHIV the correlation is equal to 0.65. Now, notice that under the conditional and dependent assumption, the correlation between Y and Z is equal to 0.12, and then you can see that the assumption is inappropriate. If we use, finally, if we wanted to measure the uncertainty of the statistical matching, notice that the maximum value of the uncertainty is equal to 0.16. Okay, when we ignore the sampling design and a no response process under the constraint that Y is less than or equal to Z, we obtain an uncertainty measure equal to 0.13. When we take into account both the process, we obtain a smaller value for the uncertainty measure equal to 0.11. And finally, I want just to show you the density estimate of the joint distribution Y and Z given X equal to 3, then for household size equal to 3. Notice that on the left, I have the density epsilon obtained from the IPF algorithm. Then when we remove, we drop the SIA, and on the right, we have the estimate of the density of Y and Z given X under the SHIA, and you can see that they are quite different. Notice that according to this density estimate, we can reconstruct clearly the final fused data set where X, Y, and Z are jointly observed. And if we estimate the correlation, we obtain a value equal to 0.55, then enough near to the correlation equal to 0.65 that we have estimated from SHIV dataset. And okay, thank you. That's all.
Thank you, Daniela. That was fast and a lot of information in a short time. Great. So, as is clear from the presentations, these are totally different topics, but they have something in common, and that's the. Yeah, could you turn down the microphone there? Thank you. But they have all non-probability in common. Artificial intelligence algorithms could potentially be used to correct for non-probability sample. My impression is that the IS data has some properties in common of non-probability sample, and the last presentation was obviously clear that it was about dealing with non-probability sample. So I will start with asking a question to every speaker, and then there's room for a discussion on the floor. Frankly, I'm a bit biased toward this topic because I'm involved in the project, so I think it's very interesting work that's been going on. But it's all at the beginning of the, so if people are really interested, they can look on the internet, but are there other options where people get informed on the progress, what is going on in this project?
Yeah, I mean, the main ones are through the newsletter. So I'm going to plug that again. As I say, on the email, on the presentation, there's our email, and we can pass that on, but my colleagues at the back there will be able to provide you with the email address too. And then within Eurostat, there is, they have a platform called Cross, and we have a section of that. Again, that's been mainly looked after by Julia at the back. So you can have a look there as well. And then, of course, LinkedIn, which we're regularly posting on that as well. So there are a number of different ways that you can get in touch. And we'd be delighted to have you join our community.
And I have a question for Marco, although I'll have a lot of remarks. The first thing about us reading the paper, I've done some analysis on AES data as well, because it's one of the biggest big data sources there, and it's intriguing, and I'm involved in a training course where we look at it. I saw you writing down that every 10 minutes, a signal is received from a different vessel, which surprised me a bit, because if I look at the raw data that we have, then it might be every 3 seconds that a signal is being sent. So my idea is that the data set you have access to is already had some form of pre-processing, although there are still errors in there, because that's the other intriguing part. AES data, it's a radio signal, and radio signals can be disturbed. And if a radio signal can be disturbed, there are 4 fields that are essential in an AES signal. That's the unique ID of the ship that can be scrambled. It's called ghost ships that may appear. So new, unique ships that suddenly appear and then disappear. They might be filtered out because that's in principle the population thing that's going on. The longitude and the latitude can be scrambled. That's the reason why those ships jump. They are not actually jumping. It's the signal that is scrambled. I have a beautiful picture on that I use in the training course, in which you see the whole of Europe. And then the Sahara is filled with ships, signals of ships, because they suddenly jump there and then disappear. You can filter them out in the way you attended. And I also realized during your presentation, there's a timestamp in there that can be scrambled as well. So that might be the reason why a ship suddenly is in the harbor and then it jumps back again. So that's and those radio signals are captured by receivers on land, but also by satellites. And sometimes a part of the data is missing. So a lot of things can go on. And this is an example of a data source for which it is very important to know how the data is being originated. That has to deal with quality issues. It's a fascinating topic. I'll stop about it because I can keep talking about it here. So what are the next steps that you're going to do, and what are your intention of using AES data for? Because that's another interesting topic.
Okay, thanks. I think that we have to be in touch about this. And okay, about 10 minutes, I made an example. I said 10 minutes, but of course there are, just to say that there is a very frequent, it is not a strict time, every time 3 minutes or 10 minutes, but they are very frequent. So you are right, there are a lot of errors inside. In fact, the example you said about the ghost ship, you said, all right? I didn't mention, but there is a kind of pretreatment. We have many records that appears once. I mean, we have one signal for one ship somewhere. So we have deleted that. So of course, we have filtered also other peculiar cases that are clearly errors. How to go on? Of course, we have to go on with the quality analysis about these problems. For instance, I've just mentioned the ships and the arrival in ports, but we have also to check the classification of the ship. I mean, which kind of vessel is, because for our statistics it's very important, and we found that there are also problems with the classification. So we need to go on with the more deep analysis. Of course, there will be a step that we will use this data as a kind of third data sources for improving also our statistics in an auxiliary mode, but we need to think also a way of using in a more statistical way this kind of data. For instance, I was thinking about some kind of estimates like capture and recapture models, but this opens other problems, because we don't need to provide only the number of vessels in a port for type, but we have also to provide other information like transportation of goods and passengers that are not into the AIS data. So in this case, we can resort to all these techniques that we have also discussed today about the use of non-probability samples for doing inferences. So I mean, this is the way we are going on.
Yeah, the thing that popped in my mind is I know my colleagues from Sweden used IS data to identify all the harbors in the country, because it might be richer than the data they have. So that's an interesting one. And now a question for Daniela, because you mentioned in your presentation you have the variable y and z, and there's no data source. There's no single data source that contains the combined set of information. So my question was, can you construct something like that? But you already did that. You mentioned that in your presentation. No?
The statistical matching, we don't have the joint information. We have on survey, on SHIB survey run by Banca d'Italia, we have a section on household expenditure, but it's not so accurate. Then it can just give an approximate information about the correlation between income and expenditure. But we wanted to reconstruct a few data sets where all the variables of interest are jointly observed. I use the correlation in SHIB just to check if the correlation when I drop this here works well.
But perhaps there's a survey that you can combine with an administrative data source. I'm from the data side, so I'm always looking for if there's a way to check your assumptions that you make. So that would be a very interesting. In the Netherlands, we have a budget survey, so people write down what they buy. And then you can combine those data, could be combined with an administrative data source. And then you can link income to it, something like that. That would be very interesting. Let's open the discussion to the floor. Are there any questions? Please indicate for whom. Okay, yeah. Danny.
Just two short questions to the first two speakers. Francesca, you emphasized how important it is that AI, ML estimates are unbiased. Now, if you don't know the answer, it's okay. You said you're not a statistician, but I'm just confused. How do you define unbiasedness when you use machine learning or
Yeah, you're right. I'm not a statistician. I don't know the answer to that question. That's why I'm relying on people like Peter to give me the answer. But I suppose, I guess the point I was trying to make was that you far more than I do, look to make sure that our samples and our surveys are not biased, and it's important when you're using AI machine learning to take the same robust approach. But how you do that, I'm going to leave to others who are much more clever than I am, and maybe Peter can answer.
I can try to give an answer, but usually it depends. If you have a statistically trained person that does machine learning, that's another story. But if you have somebody who's done data science and is not really a statistician, they just use found data, and they use a lot of found data to train a model and apply that model to the population. That model will certainly be biased. That's for sure. And the thing is, make sure that we apply a procedure that is approved by statisticians as well as data science. It's in the combination of those fields, and those are very interesting discussions, but a bit challenging. I'm glad Li Chung is involved in that as well, and David. So.
Yeah, I mean, I at a very high level, that I suppose the training of the data sets, making sure that there's a degree of obviously assurance to that. The training data sets is incredibly important. I suppose concepts like human in the loop,
Okay.
That sort of stuff. But I am not an expert in terms of the technical side. Yeah.
Is your name Marco? My understanding is that you are, at least in this presentation, you restrict interest in count data, how many ships traveled from one port to another. What about the loads? In other words, what the ships actually carry, and say if it's tomatoes, how many kilograms or whatever? Isn't that also or mostly what is really important?
Yes. In fact, this is a very good question. Of course, we have to provide also the transportation of goods, which kind of, and also the number of passengers that are not in AIS data. That's the reason why we need to do, and for sure we will have to do our survey again, but we can use in an integrated way this data for improving, let's say, the population, because we don't have a list of population that is the vessels. So for sure, we have to, as I said before, use a kind of statistical approaches, methods for estimating these quantities, like goods or whatever, by using non-probability sample, integrated, or this kind of machinery, integrating our data from AIS, from administrative data, and from the survey, because of course in survey we ask for these quantities.
Okay, Natalie?
Yeah, I just wanted to follow up on the comment because every budget survey asks their income, and I'm wondering why it's not enough to get the correlation and sort of plug that into the models. Why you need the sort of record, microdata level. You should be able to do it. All you need is that correlation, I think.
I hope that I have understood the question now, because the aim of the statistical measure is to estimate the job distribution, but this aim is connected
To build the microdata.
Okay, it can be an idea, I don't know. Thank you.
I don't know. Thank you.
Okay, there's time for a last question. Yeah,
Okay,
Marwan.
yes. Just one quick question to Francesca, another one to Daniela. For Francesca, I am ignorant, really ignorant about machine learning, but I really was interested in one sentence that was said in one of the previous talks, I suppose from Professor Kim, when he said that calibration procedures were actually also machine learning procedures with a different name. And that would make those machine learning approaches more familiar to me if there was a link between all the different kind of approaches. I wonder if already exists a kind of map between the methods that are implemented in machine learning tools and the statistical approaches, or if it is something that can be useful. For instance, for me, it would become less a black box like it is right now. And that's...
Sorry, was that that was directed to me, was it? Sorry, I didn't quite hear.
Oh, no, if there is a kind of relationship between the typical methods that are used in statistics and in official statistics and those used in machine learning, like the one that was said this morning when this afternoon when we were talking about calibration procedures, and in machine learning they had a different name, but as a matter of fact they were calibration procedures.
Okay, it's a good thought, and I don't know. It's another question I don't know the answer to, but it's something that we can definitely. I'm going to take that away and have a chat with others, but it's not something I guess as a deliverable that we're necessarily have specifically in mind, but yes, the idea is to have standard methods to do certain things using machine learning. So I think it's so I guess the answer is that yes, but we would need to figure out the equivalence, which is what I think you're talking about. Yeah, it's an interesting thought, but no, they probably thought about it, but I haven't.
The second question is about statistical matching. Daniela already knows how much I love that those kind of approaches. But as a matter of fact, I agree with Natalie that when there is additional information, it is useful to use it. But in general, in official statistics, we produce data about different topics. They are, in some sense, produced independently, although they are statistically or probabilistically linked. And the new thing that you were showing, the new aspect that, in my opinion, was important, is that when you give figures about expenditures and figures about income, as a matter of fact, you give also in some sense figures about the joint distribution, but you don't know exactly the figure that it is, but there is a kind of uncertainty on that. And that's the interval between the two distributions that you have got. But now you focused a lot, I saw, on estimating just one of the distributions in between the extrema that the Frechet bounds could give to you. But is this why it is very easy to estimate the extrema of the Frechet bounds? Is it a difficult task or not? Because in my opinion, as an official statistician, my first answer, my official answer will be, okay, the distribution and consequently the frequency that I have got in my cumulative distribution function is in between the minimum and maximum that is already justified by data. Any choice that I take from that is a kind of personal choice in some sense. So I cannot justify it.
No, yes, I say this. I say each distribution in the class can be taken as a matching distribution, and the sample data do not allow to discriminate between alternative models. But the point is that if you have an auxiliary information, you can restrict such a class if, for instance, the uncertainty measure represents a measure of accuracy of the matching distribution that you choose from the class. And then the point is to have enough auxiliary information to exclude a large part of the models from the class. I agree with you that otherwise each choice cannot be justified by the sample data.
There's time still for 2 questions, and then I would like to end.
Yeah, more a comment than a question, and to follow up on Danny's question for the problem of unbiasedness. It's actually a long answer because it depends on what is the goal of machine learning. Are we doing prediction or are we doing estimation of finite population parameters? We can have excellent predictions and still not a very good estimator of a finite population parameter. And one of the reasons is that machine learning methods, they converge very slowly and they don't converge at the speed 1 over square root of n. And so this makes, in finite samples, they can suffer from actually a fairly large bias, even though they make good predictions. And so in the literature, people have proposed double the bias machine learning, and so it's more complicated when we're trying to estimate finite population parameters. We need estimators that go at the right speed, and so people will use doubly robust estimators and so on. So that was just my comment.
There's another question, no? Okay, I suppose let's end this session and give all the speakers an applause, and then we end the day.